When it comes to levers and mechanical advantage can be the term mechanical advantage can be a little bit misleading because it all depends on what advantage you're looking to either gain or which advantage you actually have a disadvantage for. And that's all based on the geometry of the levers themselves. Now, there's three classes of levers, and we've covered this throughout our kind of mini experiments, but it's all based on the geometry, the location of the fulcrum, the effort force, and the resistance force. So first class is when the fulcrum is located in the middle. So the effort force is on one side, the resistance force is on the other. That's more like a seesaw, something like that you've typically seen. A second class would be where the resistance is in the middle, the fulcrum is at one end, and the effort is at the other. It doesn't necessarily need to have the effort, force, and fulcrum at the ends per se, but the resistance does have to be in the middle. That would be like a wheelbarrow, where the wheel's down here, you are lifting up on the handles, and the load, the resistance is somewhere in the middle. A third class lever is similar to a second class, except the effort and the resistance are flipped. The effort is in between the fulcrum and the resistance. And that would be like your bicep or your forearm. So if this was your elbow, you'd have your bicep attaching and pulling up, and the resistance would be whatever you had in your arm. Third class levers are very common throughout the body, so you'll typically see a lot of those when it comes to things like anatomy. So those are the three classes. Within each of those three classes, the geometry, the actual setup of the effort, the fulcrum, and the resistance themselves in all three classes will actually yield different advantages and different disadvantages depending on what you're looking for with the lever. And we'll get to that in 1 second. So just to take a look at this example, I'm going to use a first class lever here, and I'm going to have an effort force, the fulcrum, and the resistance. And in this case, you can see with this setup, the distance to the effort is very low, it's very small, and the distance to the resistance is very long. So my resistance is much further away from the fulcrum than my effort is. So if we go back and we talk about torque, well, the torque generated by both of these, there's a counterclockwise torque generated by this effort force, and there's a clockwise torque generated by this resistance force. I'm going to assume for the purposes of this explanation that it's in equilibrium. So it's either not moving or it's rotating at like a constant radial velocity, but it's not accelerating, so we're going to assume that we have equilibrium here. So if I have my torque, it equals force times the perpendicular distance. So if I look at this setup, on the effort side, it's this force times this distance, and that must be equal to this force times this distance. I'm not going to use numbers here, but if we take a look, this is very small, and the resistance distance is fairly large. So if these two are to be equal to one another, well, if this is small and this is large and they have to be equal, well, that would have to imply that the effort force would have to be large here and the resistance force would have to be small. So what that actually means is that a large input force or a large amount of force input by the user of this lever or by this system is only going to lift a fairly small resistance. So what that means is you have to apply a lot of force here in order to move just a small amount of resistance. So when the resistance distance is larger than the effort distance, a large input force is required to move a small resistance force or a small load. So what this basically means is regarding force, the force generated or the force magnified by that lever system, this is actually a disadvantage. I have to apply a tremendous amount of force here in order to move a small amount of force. Or more accurately, whatever force I apply here, I will always need to apply more force on the effort than the resistance force or the load. So it's a force disadvantage. I'm not multiplying my force by anything. I'm actually decreasing it. So this is a disadvantage when it comes to force. I have to generate much more force here than the actual force that I'll actually be able to lift. So with regard to force, that's a disadvantage. But if we take a look and we look at the same system, so I've taken this same lever, but now I've actually pushed it down and I've raised this load up a little bit. Well, if we don't look at the loads themselves, we look at the original position highlighted by this blue dotted line and the final position of this lever, you'll notice that the distance moved on the input side is fairly small, but the distance traveled by the load or by the resistance arm is actually fairly large. So in this case, a small change in the distance traveled by the input force translates into a very large distance traveled by the resistance arm. So whereas with regard to force, I had to apply a large force to move a small load, well, that gave us a disadvantage in terms of force, But in terms of the distance traveled or the speed, because you would assume that it takes the same amount of time for this end to go down as this end to go up, the distance or the speed of the input arm is going to be much less than the distance and the speed of the output arm. So that means with regard to speed or the distance traveled, depending on what you'd like to look at, this arrangement offers an advantage. So while I have to apply a lot more force here, and I can only lift a smaller amount of force, I can move that smaller force significantly farther or significantly faster compared to my input side. And that becomes really important when you start to look at things like anatomy, the human body, because these input forces typically come from the muscles. And muscles have a limited range of contraction. Muscles can't contract or expand indefinitely. So in certain cases, it's pretty advantageous to have a small muscle contraction generate a large amount of distance or speed covered. And that's why something like the forearm is a pretty good example. A small contraction in the bicep can actually result in a fairly large movement of the hand. And that's where this speed or this distance advantage comes in. But again, that bicep requires quite a large amount of force to even move something that may be a little bit lighter. You're always going to have to apply more force on the bicep than the load you're lifting, because the bicep, the way that's set up, where you have the effort, distance is very small. So based on your elbow and the distance to your where the bicep attaches is small. So you get a force disadvantage, meaning you have to apply a lot of force in order to move an equal load. But the advantage that you get is you can move your hand, you can move the output arm, the resistance arm of that lever, significantly further and significantly faster. So whereas one lever may be a force disadvantage, it turns out to be a speed or a distance advantage. And just to show you really quickly the same setup, but now what we've done is we moved the fulcrum, so now the effort distance is significantly larger than our resistance distance. We'll take a look at the same thing. But now our effort distance is large and our resistance distance is small. So therefore, I must have a small effort force and I must have a large resistance force in order for these torques to be equal. Well, what that basically means is that a small force will lift a large resistance. So when the effort distance is larger than the resistance distance, a small effort force will lift a large resistance load. So in this case, regarding force, this is an advantage now. Based on how this is set up, I don't need a lot of force here, and I can lift quite a large amount of force over here. This lever system, the way this geometry is set up, will multiply my effort force. So I get a force advantage. I can lift more force than I am capable of inputting, which is a good thing when it comes to force. But if we take a look at this, and we look at the original location here, and we push this down, and I look at the distance traveled, that input force had to travel quite a large distance. And even though I can move a much heavier load, I can't move it very far. So the distance moved by the input is much larger than the distance moved by the output. And again, we assume that these both move these distances over the same amount of time. So in this case, regarding distance or speed, it's a disadvantage. I can move heavier objects. I can't move them as far, and I can't move them as fast as my input force does. So in this case, the distance and speed is a disadvantage while the force is an advantage. And this is what's known as the force-speed or the force-distance trade-off. Based on the geometry of a lever, I can usually have one of these be an advantage, but it's very, very hard for both of these to be an advantage. It's possible, not necessarily an advantage, but it's possible to have something that can move a lot of force and it can move it very fast, but then you have to have an extremely large muscle. And therein lies the whole when you work out, you get larger muscles, you can perform better as an athlete, etc. But for the most part, without getting too overly complicated, there's a trade-off, because if you want to be able to lift very heavy things with a light amount of force, you're going to have to give up the ability to move them great distances. And if you want to be able to move them great distances, as shown by this example, where to go? If I want to be able to move it great distances, or I want to be able to move them very fast, well, I'm going to have a force disadvantage. I'm going to need a lot of force to do so. So it's very hard to get a lever system that magnifies the force of something while also magnifying the speed. It's the trade-off. You'd have to choose between the two. And you're always either going to have to generate a lot of force or you're going to have to generate a lot of speed in order to get what you're looking for. So it's called the speed-force trade-off. And just to show you, it also happens with the other lever systems as well. If I have a third-class lever here, the effort distance here is small, but the resistance distance is large. So that means if this is small and this is large, my force on the effort side must be large. My force on the resistance side must be small. So a large force is required to move a small load. And on the other side, if we look at the distances traveled, well, the effort force only travels a small distance, and I get a much larger distance. So this would be a force disadvantage and a speed or distance advantage for third class lever. And if I look at a second class lever, again, the resistance distance is small and only goes from here to here. The effort distance is large. It goes from here all the way over here. So if this is large and this is small, the force is required in order so that the torques are balanced. I must need a small effort force and a large resistance force. So this tells me that a small input force will effectively raise a large output force or a large load. But again, the resistance is not moving very far. The effort has to move very far. So I can have one or the other. I can't have both. I can have speed or distance moved, or I can have a much greater load moved relating to the amount of input force put in. So it's called the force speed or the force distance trade-off. I can have one based on the geometry. I can't have both. I'm going to have to decide which I want and design my lever system that way.